Okay, more trig in real life. As the seasons go by, if we have like 12 o'clock midnight and then 1, 2, 3, 4, and so on up, the sunrise goes from happening very late in the middle of the winter to coming earlier in the spring, very early in the summer. In the middle of summer, the sun comes up in Edmonton almost 5 o'clock or even a little before that. And then in the fall, it starts to get later and later and later, and until in the middle of winter, it's more like 9 o'clock or pushing 10 before the sun is over the horizon. And it turns out that pattern follows a fairly ugly trig equation, which they've given us here. Not too nice. So T is the time that it is when the sun comes up, and D is the day of the year. So January 1st is day 1, and January 31st is day 31, February 1st is day 32, and so on until December 31st is day 365. So write a suitable window that could be used to graph this thing. Well, I kind of wrestled with that when I was doing my axes up there, but if we have to do it for real, the earliest the sun could possibly come up is midnight, so putting 0 as your minimum is generally a good habit anyway. And I suppose you could go all the way up to 24 if you wanted to really go nuts on the vertical axis. I think it would be safe to stop at 12. I don't believe there's anywhere in Alberta where the sunrise happens later than noon. So going 0 to 12 will give you nice regular tick marks. It'll be easy to find 6 o'clock because it's right halfway up. So that should be pretty good. And on the horizontal axis, you want to start at 0, which represents New Year's Day in the morning. And you'd have to go up to at least 365 to cover a whole year, because that's the period of this function. We know it's the period of this function, incidentally, because we know how seasons work, and also because, look at this b value they gave us. This is interesting, and this is something that happens kind of often when we're doing trig expressions. The b value they've given here is actually 2 pi over 365. Now we know from our formula that the b value is supposed to be 2 pi divided by the period. And normally we put this number in and we actually do 2 times 3.14 divided by the period and we get some nasty decimal. But experienced mathematicians will sometimes just write the b value like this. They won't calculate it and turn it into decimal form. They'll actually write 2 pi over, and then they do this. And this is nice because now just at a glance you can see what the period is. If the period is 365, this is what you write for b. If you have something that happens every 24 hours, then for your b value you put 2 pi over 24. And then people at a glance can see that the period of this thing is 24 hours. So when you see this 2 pi, it's not us messing with you and just trying to make you do more work on the calculator. We're actually slipping you the period without you having to calculate it out. It's actually a helpful thing that math people do for each other. So if you get a decimal, fine, do 2 pi divided by b and you'll get the period. But if we write it this way, that's someone helping you out, telling you the period's 365 days. Now, let's see how we can use this thing. Use the formula to determine to the nearest minute when the sun rose on May 7th. Oh, and I was about to do 31 plus 28 plus 31 and crunch out which day of the year this is, but they're telling us it's the 127th day, so that's nice of them. The time for sunrise will be minus 1.79 times the sine of 2 pi over 365. Our day is number 127 minus 78, and then we add 6.3 on the end. So now we bash at our calculators to get that. 127 minus 78. I'm not using a programmable calculator, so I'm doing this in bedmass order myself. Your procedure may vary a bit. Times 2 times pi divided by 365. Before you hit sine, make sure you're in radian mode. Remember, as soon as we said 2 pi up here, we were committing to working in rads for this entire thing. So make sure you're in radian mode before you do the sine. And then you multiply the result by negative 1.79 and then you add 6.3 to that, and I get that the sunrise time is 4.96 hours. Now that's 4 plus 0.96 times 60 minutes. So it looks like it's about 58 minutes. This sunrise would happen at about 4:58 a.m. And for part C, determine on which days of the year the sun rose at 7 a.m. This is going to take more space than I currently have, so excuse me a moment while I hack out some more room. We're going to have to draw some axes and things here. Okay, so we have our sunrise formula, which says the sunrise time. Oh, where are we here? There we are, sorry. Our sunrise time is minus 1.79 sine 2 pi over 365 times an unknown t minus 78 plus 6.3, and we want that to come out to 7 on the nose. So we have to solve this for t. If we subtract 6.3 from each side, we get minus 1.79 sine yada 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 t minus 78 equals 0.7. That's 7 minus 6.3. Then we divide it by minus 1.79, and we get sine all this stuff. T minus 78 equals 0.7 divided by negative 1.79 is negative 0.39. And now we're going to do the trig part where we draw axes. Pretend for a minute that this just said sine theta equals negative 0.39. What would you do? You draw axes. You go, okay, they want sine to be negative, so I must be either in this quadrant where sine is negative, or this quadrant where sine is negative. And now to get our reference angle, I'm going to do on the calculator inverse sine 0.39. I'm not going to tell it about the negative, or it'll start trying to help and just make a terrible mess. So just say positive 0.39. So when you do that, it's second sine 0.39. It comes back with a reference angle of 0.402. And that reference angle could be in the bottom left quadrant, or it could be in the bottom right quadrant. Either one is valid. So those are our reference angles in the two quadrants where sine is negative. Now, we don't want reference angles, we want actual rotation angles, and that means we have to do some adjusting here. The two angles we could really have are over here, pi plus 0.402, or going way around to here, we could have 2 pi minus 0.402. So let's see what we get for those. We get either theta is pi plus 0.402 is 3.544, or the other possibility is theta is 2 pi minus 0.402, which is 5.881. So those are the two angles that we need. And if this equation were just sine theta equals, we would be done right there. Those would be our answers, and we'd be on to the next question. The trouble is, the argument in here isn't just theta, it's all this. It's 2 pi over 365 times t minus 78, so we've got a ways to go again. We actually have to do, I'm just going to switch colors one more time. Instead of theta, we actually have 2 pi over 365 times t minus 78 equals 3.544. And now I have to try to fit all that in again. We have 2 pi over 365 times t minus 78 equaling 5.881. So we have to solve each of these to actually get values for t. So, forgive me if I fast forward this a little bit. I'm just going to work this on the calculator and let you know when I get a final result. Feel free to follow along, and we'll talk in a minute and see if we got the same thing. Dividing by 2, dividing by pi. For this left one, I get t minus 78 is 205.9. And then we add 78, and we get t equals 284. For the one on the right, 5.881 times 365 divided by 2, also divided by pi. And we get t minus 78 equals 342. And then we add 78, and that's a little awkward. We get 420. We'll deal with that in a moment. So, which days are these? This is not trig, and if you feel like skipping this section because it's not trig, I don't blame you, but I'll show you how you work this out if you don't feel like pulling out a calculator, or a calendar, I mean. January 31st is day 31. 28 days after that is the last day of February, so February 28th, add another 28 days onto there, that would be day 59. March adds another 31 days, that brings our total up to 59 plus 1 is 60, plus 30 is 90. April has 30 days, that brings us up to 120. May has 31 days, that brings us to 151. June has 30 days, which brings us to 181. July has 31 days, which brings us to 212. August has 31 days, which brings us to 212 plus 31 is 243. We're getting close. September has 30 days, which brings us to 273. And we're not going to make it to the end of October, so let's stop and think here. At the end of September, we're at 273 days. 11 more days will get us to 284, so I'm going to say that this happens on October 11th. 273 days to get to the end of October, and that leaves 11 more days, which gets us 11 days into October. Now, here, the formula messed with us a little bit by giving us 420, which is more than a year. But since these sunrises happen basically the same day every year, that doesn't hurt us as much as you'd think. If you have 420 days, we're just going to say, okay, take a year off of that, just so we don't have to count through a whole year to get to where we're going. And we find day 55 of the year is where this second event occurs. Which day is that? Well, let's see. If February 28th is day 59, then back up a day. The day 58 is the 27th. Day 57 is the 26th. Day 56 is the 25th. And day 55 should be February 24th. So, just going into winter, we get a day where the sunrise is 7 o'clock, and then just coming out of winter, we get another one. October 11th and February 24th. There might be a faster way to count out to the February 24th, but I'm a little bit tired, so I couldn't think of anything better than this at the moment. Getting out a calculator is, or I keep saying that, getting out a calendar and actually counting out days is very easy if you happen to have one nearby. Now, determine the period for this function. I ruined the surprise there. The period is 365 days. They told us that by using that customized value for B. Write a suitable window that would display this graph. We did that. And Oh, the rest of these are from the assignment, so we don't actually need them.